Hi guys, this is Matthew Burns. I haven't made a video in the longest time, but I finally got back to working on projects now that I'm settled down in Texas and I'm done with school. Not really, I'm actually doing a master's, but I'm kind of done with school. And I'd like to introduce you to the next project that I've been doing. And I'll be showing the schematics of it, the board layout, and talking about what I did. I'll also be posting the schematics and the Gerber files on my website at bunchofelectricals.com. So if you're interested in replicating this project or taking a look at the schematic or using it for your purposes, feel free. I just honestly, this board I made to assist myself in making other boards. I know there are 1,000,001 development boards out there. There's, a Raspberry Pi and Arduino or whatever. But I'm really fond of the PSoC. So I wanted to make a board that is very simple. It connects to power, so I want to use a barrel jack, something that plugs into a wall so I don't have to be using my lab supply every single time I want to turn the thing on. I wanted it to connect to my laptop for easy debugging purposes. I used to use this little Bluetooth module called the HC06 so that I can write UART to it from some sort of a microcontroller or FPGA or whatever, and pick that up with a Bluetooth dongle on my laptop in Pi serial in Python and plot it out. But that got to be a real pain in the butt. So I want an easy connection to my laptop, so I have an Ethernet connection. And I want GPIO pins. I really like the PSoC microcontroller. It's kind of a microcontroller. It's really a system on a chip. It has reconfigurable analog and digital inside it, and you can reroute basically whatever you want to basically whatever pin you want. So it's honestly a really great microcontroller that's super configurable and you can use for whatever you like. So I used to use a development kit they had for like 14 bucks. It was a PSoC 5, but I wanted to put my own PSoC on this board, and the one that I picked, I have to say, is probably like the cheapest one there is. I did that because this board that I made, before I decided I was going to use it to help me develop further projects or other projects, future projects, it was going to be for a Ethernet controlled robotic arm that I was going to use for a class that I was going to teach in person, but I may or may not still use this for that. This board's fine for that. The problem is, I'm afraid it's a little bit too complicated for like middle schoolers. So I may end up having to do that class breadboard style and very simple potentiometers, inductive load drivers, and a stepper motor. But today I want to talk to you about this board. So what I have here is 5 pages on this schematic. It's not terribly complicated or long. This first one here is power. So I bring power in through a barrel jack. I have some input capacitance. I don't really do too much to filter the line, but I don't really need it for this small application that's not drawing a lot of power. I have this switching converter here. It's the LT8650. I decided to use this switching converter because it has 2 outputs, one at 5 volts and one at 3.3 volts. So there are 2 buck converters on this thing, hence those 2 inductors there. And the real reason why I wanted 2 outputs, even though everything on this board is controlled at 3.3 volts, is because I have an Ethernet communication and I have a microcontroller. And the microcontroller is the PSoC. The PSoC's programmed through JTAG. Perhaps you guys may know that this is not a problem, or you may know that it is a problem. I haven't heard regardless, and I've been searching around online and I haven't found, so in the comments, if you see this video on YouTube, please feel free to let me know. But what I was concerned with is I was concerned with hooking the JTAG programmer up to my microcontroller. The JTAG programmer, say, can supply 100 milliamps. The microcontroller, let's pretend, pulls 50. I didn't want current flowing through the reverse body diode and the high side FET of the switching converter and having to charge up the big bulk caps I have on the 12 volt input line through that jack, or powering, well, it probably wouldn't power the stuff on the downside of that other 3.3 volt switching converter, but I really didn't want any current draw from pre-switching converter. So what I did was I had a switching converter that has a 5 volt regulator and a 3.3 volt regulator, and then I used a linear converter, which is like a BJT kind of on the inside, so current really isn't going to flow backwards, to step that 5 volts down to 3.3 volts. Also, it provides me a clean 3.3 volts with no real noise or anything like that, ripple on the output. So, sorry, I haven't made a video in a while. This is probably not great, but let's roll with it. So I have this switching converter here that provides me two outputs, a 5-volt output and a 3.3-volt output. The 3.3-volt output is accessible right here. The 5-volt output's accessible right here. And then I use this switching regulator to step the 5 volts down to 3.3 volts. So I have two isolated 3.3-volt supplies that share a common ground. And that's it for my power supply. For the microcontroller, there's really nothing to show on this page. It's a PSoC. It's the CY8C5467LTI LP003. I picked the cheapest one I could get because we were going to have to make a whole bunch of these for a bunch of people I was going to teach this course in person to. Except I wasn't actually going to teach this board. I was going to use this board to control a robotic arm, and elements of the robotic arm we'd discuss, talk about, and teach. So perhaps it's not the best fleshed out plan. Still working on it. But that's what this was initially intended for, so if I was going to have 50 of these made, I wanted it to be cheap. It's like a $2 microcontroller. Perhaps there's a pin-for-pin compatible higher-end PSoC that you could switch out, or you could change the schematic and change the Gerbers. It wouldn't be that complicated. It's only one section of the board. That would require me to post the Eagle file. We'll think about that when we get to it. So all of the power lines on this, I have ferrite beads and capacitors on each power input of this microcontroller, so that any high frequency noise that it generates doesn't get back into the rest of the circuit. Any high frequency noise in the rest of the circuit doesn't get to this. It has a nice filtered supply. And this particular chip has a ground pad on the bottom, so I have a really solid ground connection, electrically and thermally, but a really solid ground connection with a whole bunch of vias on the ground plane. So I don't expect problems with ground bounce of the chip turning off due to too much current being drawn, the line voltage dropping. Also, this chip can operate down to like stupid low voltages, so I really don't foresee any problems at all. All of the pins that aren't tied to ferrite beads or capacitors are either JTAG programming port, which you can see there where it all says prog and stuff, and then general purpose input output pins that are on this chip reconfigurable as analog or digital. And we'll get into that in another video series. I just wanted to go through the electronics of it today. The next part of the circuit is the Ethernet portion of the circuit. I did lie. There are some other pins on those microcontroller that connect to this Ethernet controller. So master out, slave in, master in, slave out, serial clock, chip select, reset, and the interrupt line, which is controlled by this microchip Ethernet controller, the ENC28J60. It's one that I've been using since I was in, I don't know, middle school or high school. And I had this, I don't know where it is right now. I may still have it, but this little development board version, here it is actually. Ha. This little development board version that has pins that you can connect to. It's this slick little controller. It's 20 megabit per second serial peripheral interface communication with it. So, and it's 10 megabit per second Ethernet. So if you want something that's high bandwidth, this isn't the chip for you. But if you're working on a project and need to be able to see what's going on in the circuit or communicate with a computer, it works perfect. Perhaps someday I'll upgrade this board to include gigabit Ethernet. Also, again, you can see the power supply lines are filtered with ferrite bead and 0.1 microfarad capacitor. I have the magnetics, the RJ45 jack, resistive terminations to the 100 ohm differential impedance line. So that's all on this page. Here I have the JTAG programmer. So it's pretty standard JTAG looking connection. One thing I did was I'm using that linear regulator as the last regulator on the line that powers the microcontroller. So when the JTAG programmer hooks up to power the microcontroller, whether the microcontroller is powered externally or not won't matter, because power isn't going to flow back into the rest of the circuit, break the JTAG programmer. Also, there are ESD protection diodes, I believe. I actually haven't looked at the datasheet because I'm honestly allergic to that. But there are ESD protection diodes, I believe, or in case there are in this microcontroller. I didn't want to, if for some reason I didn't have power externally selected on if for some reason I didn't have power from the JTAG programmer being supplied, but I had the JTAG programmer plugged in and I was trying to program, and the chip wasn't powered externally, I didn't want current to flow through the ESD protection diodes from these programming pins and power the rest of the chip, draw a whole bunch of current through those ESD protection diodes and break them. So I put current limiting resistors on them, just something small, 100 ohms. It'll probably save the diode, it'll probably save the chip. It can handle the amount of, it's 3.3 volts over 100 ohms is what? Dumb small amount of current. It'll be fine. So there's my JTAG connection. The only problem I've encountered, I have had this board made, so I'll kind of break the surprise and I'll show it to you as soon as we finish going through the circuit, which we're almost done with. The only problem I had with this circuit, and I'm posting these files right online. So one thing you want to be aware of if you're going to use my schematic or Gerber for this is that there was a problem with the routing to this JTAG programmer. The routing was fine, it was great, but I messed up the rotation, and not the rotation actually, I want to say the chirality, and I don't know if that's the word electrical engineers use, but you know what I'm saying, of the JTAG socket on my board. So it's not like I could rotate it 180 degrees. I actually need to like mirror the connections to the JTAG programming terminal. So what I ended up doing was I didn't end up changing the board in the slightest. I took my JTAG cable, and since they're cheap and you can buy them from SparkFun, DigiKey, Mouse, or whatever, I cut it up and I rewired it. So it's working for me, and that's something you'll just have to be aware of if you choose to use this schematic. It's the only problem I've encountered so far. The board's still pristine, and guess let's keep going. So the last part of this board is rather simple. This is just a board-to-board connector. It's a board-to-board, yeah, it's a board-to-board connector so that I'm routing all the GPIO pins of the microcontroller to, in addition to 12 volt power, 3.3 volt power, and ample ground. I have, it may not look like it based on the way the pins on the schematic symbol map to the pins on the footprint, but next to every single GPIO pin that goes across this board-to-board connector, I have a ground connection. So I did that because I wanted to minimize, I wanted to have a solid ground return path, and I wanted to have the ground return path not shared by too many pins because I don't want to have a huge amount of crosstalk due to the ground return for two different pins going, for two different GPIO going through the same ground pin. So yes, it will happen a little, it's kind of minimal, this connector is rather small, but I have really solid ground connection tied, interspace between all the GPIO pins, as well as solid blocks of ground connection for the 12 volt and 3.3 volt power. So that's it for this board. It's, to recap, it's you know, a power circuit that you take 12 volts in through a barrel jack, or honestly the switching converter can take like what, like 12 to 40 volts or something. So some kind of input through a switch, through a 2.1 millimeter inner diameter, 5 point whatever. You could look up the part number. I'll post the schematics. There's the part number. Outer diameter. And it generates two 3.3 volts supplies that are isolated. One of them is has a linear regulator output, so I'm using that to power the microcontroller. I have the microcontroller. I have the Ethernet controller, so you can control this thing with your laptop. I have a JTAG programmer, so I could program the board. And I have GPIO connection. So it's really just a PSoC breakout that's Ethernet controlled and plugs into the wall. So that's kind of all there is to it. I'd like to show you a little bit of the board layout that I have. So I guess it kind of looks like this. I have most of the layers hidden. Let me show them. So let's turn all of these on, then I'll turn them off one by one. My keyboard. Run the rat's nest command. There we go. So the board looks like this. The top layer, the stack up that I have, it's a 4-layer board. The stack up looks something like this. I have, I assumed it was 0.035 millimeter copper thickness. I forget what ounce that is. It's some, whatever, choose your units, or 0.05 millimeters, I figured, because it would grow a little bit after plating. Started at 0.035. Prepreg, 2 layers of it at 0.15 millimeter between the inner layer and the outer layer, so 0.3 millimeters of prepreg and a 0.7 millimeter core. So that's the stack up that'll give you 100 ohm differential impedance on the lines that are impedance controlled. The top plane, let me zoom out, wow. The top plane is a power plane. I bring in 12 volts through this connector here. 12 volts goes around to the GPIO breakout up top. I step that down through this buck converter, which has 2 inductors, which you see are kind of close in proximity. So I rotated them at 90 degrees to each other to have minimal field overlap, so that one's not really, they're not coupled. I tried to, because they had to be close, I tried to make them as not coupled as possible, so they're rotated at 90 degrees. This one provides the 5 volt output, and the feedback's right here. This one provides the 3.3 volt output. The feedback's also going underground, but right here. And then I have the linear regulator right here that steps that down to 3.3 volts. So this is a 3.3 volt plane, and this is a 3.3 volt plane, but they're isolated. Here's the Ethernet controller, the magnetics for the Ethernet controller, and the routing to the RJ45 jack. Here's the JTAG programmer, the PSoC, and the GPIO Breakout. And that's it for the board. It's quite simple. Now, let's hide some layers. So there's the top layer. The next layer is ground. So I have 2 grounds. It goes power, ground, signal, ground. I do have some signals on this ground plane. This ground plane was kind of secondary. I really only had a ground plane at the bottom and an XY routing pair, but then I realized I didn't need the XY routing pair because I used pin swap and had minimal, because I used pin swap and had really minimal routing. So I had really no crossing traces, except for a little bit by this RJ45 connector. So I really didn't need this second plane to be a ground plane, or I didn't need this for a signal layer for XY routing pair, so I used this for another ground plane. Below that, I have the signal layer. It's the orange. And you can see there is the Ethernet connections, from the RJ45 to the magnetics, and they're impedance controlled, but they're short, and honestly at 10 megabits per second it doesn't matter. You can do whatever you want to those traces. If they're that short, 10 megabits per second, you're not going to hurt it. But I did a good job nonetheless. Going to the Ethernet connector, you can see here are the SPI connections from the Ethernet controller to the microcontroller, and the rest of these, all just routing up to this GPIO breakout, are GPIO pins, the microcontroller. You see, the first thing I do is I have stringers bring traces underground to the signal layer, and then I move them over to the GPIO breakout, bring them back up, and attach them to the connector. If you take a look at the connector, one thing I was very careful to do was, with via placement, I wasn't going to get really wide vias so that I can do blind or buried, because their ratios, the ratio between the drill depth and the drill diameter is very constraining. So if you have a decent thickness board and you want a buried via, you're going to have a really thick via. And I really didn't have, this is a really small connector. This has 80 connections on it, which honestly, in hindsight, was a mistake, having a connector this small. If I want this to be easily accessible, I should have had this connector be twice as big, 4 times area-wise. Let's talk past that. This connector's small. I couldn't afford having wide vias. So everything is through hole. So I had to make sure that where I had vias, I wasn't breaking up the ground plane connection to this connector, because this connector attaches to ground. But if I had like a solid chopped up ground plane where there was no ground connection from here to here without going all the way around, the ground return for all these pins would be all the way around here, and there'd be massive amounts of crosstalk radiation, and it would suck. So let me see if I can zoom in a little more. I did a pretty good job. I hope you may disagree. I did a pretty good job making sure that these vias were placed appropriately, that there was respectable. It's not great. Yes, there will be changes in impedance when the line goes off of the ground plane, but that has to happen because these vias don't connect to ground and they're through hole. There's nothing I can do about that. Other than that, there's ground plane under the trace, and there's respectable, even if the ground plane current return has to detour, it's very minimal. So I don't expect there to be a whole ton of crosstalk. This is a very small connector. I'd say it's pretty good. If you guys have comments on it, I'm getting better at this as I go. If you guys have comments on routing, layout, or anything like that, let me know in the comments. On YouTube, I really don't have a blog on my website yet. I should. So those are the 4 layers of this board, and that's kind of all there is to the routing. So I had this board made, I had it assembled. I'm using 0201s in this board for my resistors, capacitors, ferrite beads, and frankly, those are really, I've tried to work with them, I've failed working with them. I can't solder 0201s. I can solder 0603s all the time. I can solder 0402s like half the time, maybe 3/4 of the time. I can't solder 0201s. I've never successfully got it. But I do have a completed board nonetheless because I had these assembled for me, and they frankly look really good. So here's the board completed. You can see the Ethernet connection, the power connection, the power converter. I don't believe in ESD. That's the only reason why I'm holding this. Power converter, the magnetics for the Ethernet controller, and the PSoC and the RJ45 connector. So, and I can also provide you these STL files. I 3D printed a case that takes threaded inserts that I can smush into here. It holds nuts on the bottom for mounting these standoffs, and it's a perfect fit. It lines up. I don't yet have the 4-40 threaded machine screws to hold these down to the standoffs, which is really stupid. They're M3 on the bottom side of the standoff, and they're 440s on the top side of the standoff. I'm not mechanical. I may be saying that wrong, but you know what I mean. The 4-40 machine screws. I need one that's like 3 or 4 millimeters or something like that, or 3/16 of an inch. But it's a really perfect fit. I also have a lid for this. It's in the other room. Let me see if I can grab that for you real quick. So you see it's a really snug fit. You just thread those screws down into the inserts and it holds itself closed. It's a great looking little board, and it'll let me... What I plan to use this for is I plan to use this to speed up development of all my future boards, because it has the overhead of making circuits done. When I'm testing something that I want to test that I'm not necessarily going to make for like a Matthew home product that I'm just going to like use in my house all the time, it's just some cool science thing I want to test, I need power for the board. I need communication with a microcontroller. I need to be able to debug it. You know, so I have the Ethernet communication so I can easily debug it. I have the GPIO pin reconfigurable, analog and digital. And one thing my professor said to me is, like, if you were stuck on an island and had one microcontroller to make something work, it would be the PSoC, because the thing is, the PSoC has reconfigurable hardware inside it. It's not just, it's a whole system on a chip. And it's not just reconfigurable digital hardware. It's not like some FPGA. It also has reconfigurable analog that you can reroute to different pins. So if you're missing some analog hardware that you really need to make something like a feedback loop or whatever work, this chip is, you can configure it to have that hardware inside it. Just provide something like a resistor or whatever to make your feedback loop work attached to the GPIO pins, and you're good to go. So if you were stuck on a desert island and you needed some chip that could do something useful, it would definitely be the PSoC. No, I have no sort of deal with PSoC in this matter whatsoever. I just think they're great. And yeah, so that's it for my board. Let me show you the programmer that I'm using for this, and in the next video we'll get into honestly probably just turning it on to see if it works, or maybe I'll do that in this video. So I went ahead and I couldn't find them on DigiKey or Mouser, but I did find them on Cypress website. I bought this Mini Prog 4 and it seems to be working for me, but I haven't really programmed it too much. here's the cable, the JTAG cable that came with it. I did have to cut it up so that I could route the correct wires to the correct pins, and then I taped each one individually and taped over all of it. But it seems to be working pretty great. So all there is to it is I just plug this into here. I plug the other end into my board on the JTAG programmer. Here, let me try to... While I was talking to you, I was just being goofy, and I started threading some of these machine screws into the case with my hand, and now I can't open the connector. There we go. You just take this cable, you plug it into the JTAG connector here, which, yes, does have its chirality kind of backwards and messed up, but whatever. I'll change the angle of the camera, and I'll show you that this thing is capable of being programmed. I haven't yet written driver software for the ENC28J60 yet. I'll be doing that next. So the first thing you need is a USB connection. And the Mini-Prog 4 comes with this USB to micro USB cable. You plug the micro USB cable into the Mini-Prog 4. Doot 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 doot. Sounds like on your computer. Then you can go to PSoC Creator, which I actually already have open. Let's get rid of Eagle because it served its purpose. And PSoC Creator is great. It's for developing applications, software, whatever on the PSoC. And it lets you reconfigure the hardware inside the PSoC on this .cysch sort of schematic file. I'm assuming that stands for Cypress Schematic. But it lets you drag different analog things, digital things, whatever, onto the board, communication, and then there are APIs to just interface with that hardware. I'm not going to be using any of that right now. I just want to show you that I can program this thing. We'll move on to what we're going to program next time. So here in main.c, the file main.c will start up with most of the stuff in it because there's mostly nothing in this file. It has, you know, I'm not a C person. I just make things work. But it has the main loop right here. Interrupts, global interrupt flag is enabled. It has the main loop here, and in the main loop is where you write your software to interface with the API that runs these, that runs these schematic hardware pieces. I just have some dumb loop that adds some integer to 1 every single time around the loop. And the only reason why I'm doing that is because I want to ensure that I can actually program my microcontroller. So if you look down here, you'll see that I already programmed it, and it says it was successfully programmed, but that's not really good enough. So I'm going to do it again for you. So the first thing you do once you create your schematic in C file, main.c, that's going to run your PSoC, is you go up to build, and then it shows your project name. So mine's Internet PSoC Breakout. Stuff will run down here, and it'll say something. Build succeeded. I don't know if you'll be able to see that on YouTube or not. So the thing is, I may be zooming in way too much. It may be super easy for you to see, but I don't know. So then you go up to debug, program, and before I click it, I'm actually going to just angle that down there so you can see what it says when I click it, and I'm clicking it now. It's doing a whole bunch of stuff, and there wasn't a lot to program. It's a single line of code I had, but it says the PSoC was successfully programmed at a date and time. So that's really it for my Internet PSoC Breakout. It's programmable, the circuit's great. In the next video I'll be talking about some driver software that's going to connect my thing to my desktop, and I'll also have a schematic file because I'll need a serial peripheral interface block to talk to it. I hope you guys enjoyed this. I know it wasn't crazy in depth because I can't do V equals IR for every component on this board anymore. But I'll be posting schematic files at bunchofelectricals.com. Between every word there's I don't know if it's a hyphen or a dash. It's like that horizontal line that's kind of in the middle. Bunch, I'll call it like a dash, bunch dash of dash electricals.com. And if you guys are interested, you could download the schematic files or the Gerber files if you wanted to send this out and order it yourself. I'll actually probably post a bill of materials. I can post the Centroid file because some board houses are going to ask for that. The problem is the Centroid file will tell the board house, if you're going to have it assembled, where the parts go and how they're oriented. I just had the Centroid file auto-generated by Eagle. I didn't put much effort into it, so I had to visually confirm with them the orientation of parts. So the Centroid file may not be 100% correct. One known error with it is that the part labeled as Q1, I don't know why it's labeled as Q, frankly. It was default from the DigiKey Snap EDA, is my oscillator for the ENC28J60, my 25 megahertz oscillator. That part was rotated 180 degrees when they assembled, so I suspect that there's a problem with the Centroid file there. And the connector for the JTAG programmer has its pin numberings wrong on the schematics, so you're going to have to modify your JTAG cable if you want to use these designs. But all of that's straightforward and easy. I'll probably come out with a second version of this. I don't know exactly when, because this is working for me, but the board's still pristine. So if you guys want to use it, you're welcome to. I'll post all my files I had to make this, but keep in mind what I said during this video about the Centroid file and the JTAG connector. So that's it. I hope you guys enjoyed this. Maybe some of you will find it useful. If you download the stuff from the website, just let me know in the YouTube comments, or don't. I don't care. I just like to see if anybody's actually making use of it or whatever. If anybody thinks it's cool. Maybe I'm stupid. Anyways, I'll see you guys in the next video tutorial where we talk about the software and connecting to your laptop. Thanks much, and hope you enjoyed this video.